Imagine trying to take a clear photograph through a very misty window, or attempting to capture a precise sound through a thick, vibrating wall. In both scenarios, the information you receive would be significantly distorted and unclear. Remote sensing signals encounter fundamentally similar challenges because Earth's atmosphere profoundly influences how they travel from a target on the ground or in the water, all the way to a sensor positioned in an aircraft or satellite. These atmospheric effects actively scatter, absorb, and refract electromagnetic radiation, fundamentally altering the quality and accuracy of the valuable data we strive to collect. The atmosphere is far from an empty void. It is a complex and highly dynamic mixture of various gases, primarily nitrogen and oxygen, alongside varying amounts of water vapor, tiny aerosol particles, and fine dust. When electromagnetic radiation, such as visible light waves, infrared energy, or radar signals, journeys through this medium, it inevitably interacts with these atmospheric constituents. Scattering occurs when radiation is redirected and diffused by particles or molecules, causing a change in its original path. This can lead to a hazy appearance in images. Absorption, on the other hand, takes place when atmospheric gases effectively take in and retain specific wavelengths of energy from the radiation. Both scattering and absorption work to reduce the overall signal strength reaching the sensor, and they can significantly introduce visual haze or blur into remotely sensed images. The amount of water vapor and the concentration of aerosols, both of which fluctuate considerably with local weather patterns and global climate, play a particularly significant role in determining the magnitude of these atmospheric impacts on the signal. For professionals and researchers working diligently with satellite imagery or airborne sensors, a deep understanding of these effects is absolutely crucial for accurate and reliable data interpretation. Remote sensing scientists employ a sophisticated array of techniques to meticulously correct for atmospheric distortion. These methods commonly include advanced atmospheric correction algorithms that computationally model precisely how light and other radiation interact with various atmospheric components. Furthermore, radiometric calibration methods are applied to normalize the sensor data, ensuring consistency. By diligently applying these essential corrections, researchers can ensure that any changes observed within the data truly reflected genuine surface features and phenomena, rather than merely atmospheric noise or interference. This rigorous process allows for incredibly precise measurements of parameters such as vegetation health, ocean temperatures, or the expansion of urban areas. A particularly vital concept in this field is atmospheric windows, which refers to specific wavelength regions where electromagnetic radiation can successfully pass through the atmosphere with minimal absorption or scattering. Satellite sensors are often expertly designed to operate predominantly within these windows, thereby optimizing their ability to collect high-quality data. Another critical consideration is understanding path radiance, which describes the electromagnetic energy that is scattered directly into the sensor's field of view by the atmosphere itself, without ever having interacted with the Earth's surface. Ignoring this path radiance can unfortunately lead to a significant overestimation of the inherent brightness of surface features, which can severely impact any quantitative analysis or scientific findings. By comprehensively recognizing and diligently accounting for these complex and dynamic atmospheric interactions, remote sensing professionals can effectively transform raw, unrefined signals into highly reliable, scientifically sound, and actionable data products. This systematic and meticulous approach empowers us to accurately monitor Earth's continually changing surface and environment, providing invaluable support for critical decision-making in diverse fields such as environmental management, sustainable urban planning, and rapid disaster response efforts.